Let's take a look at a specific kind of series, the geometric series. Recall that a geometric sequence is one in which each term is a multiple of the previous term. In other words, they are of the form a times r to the n, where r is not zero and is constant. A geometric series, then, is the sum of the terms in such a sequence and is written as the sum from n equals 0 to infinity of a times r to the n. Just like any other series, a geometric series is going to converge if the limit as n goes to infinity of its partial sums converges, and it's going to diverge when that limit diverges. So let's see if we can figure out what the partial sums of a geometric series look like. In order to examine the nth partial sum of a geometric series, we're actually going to look at the n plus first partial sum. So recall that s sub n plus 1 is the sum of the first n plus 1 terms in that sequence. So we're going to get a times r to the 0 plus a times r to the first plus all the way out to a times r to the n. We stop at n because we're including the 0 term, so that's n plus 1 terms. Now, notice that the first term is just a, and then we have a times r1 plus all the way out to a rn. We're going to do something clever here. We're going to factor out an r. So we can rewrite this now as s sub n plus 1 is equal to a plus, if we pull an r out, we get a times r to the 0 plus a times r to the first all the way out to a times r to the n minus 1. All of the r exponents will drop down by 1 when we factor that out. Notice then that this expression right here, this is the same as s sub n. So in other words, we just found that s sub n plus 1 is equal to a plus r copies of s sub n. We also know by the definition of the nth partial sum that s sub n plus 1 is equal to s sub n plus a times r to the n. The last term gets added on each time. So here we have two expressions for the same quantity, which must mean that they are equal to each other, which gives us the equation a plus r s sub n is equal to s sub n plus a r to the n. Our goal here is to find an expression for s sub n. So what we'll do is get our s sub n terms on the same side. So we'll rewrite this as s sub n minus r copies of s sub n on the right, and that gives us on the left a minus a r to the n. On the left, I'm going to factor out an a. On the right, I'm going to factor out an s sub n. We're going to solve this for s sub n by dividing both sides by 1 minus r. And so now we see that s sub n is equal to a times 1 minus r to the n over 1 minus r. All that's left for us to do is evaluate the limit as n goes to infinity of these partial sums, and then we'll have an understanding of when geometric series converge and when they diverge. So, given that our partial sum is equal to a times 1 minus r to the n over 1 minus r, if we evaluate the limit as n goes to infinity of s sub n, we're taking the limit as n goes to infinity of a times 1 minus r to the n over 1 minus r. The only quantity that's going to change in that expression as n goes to infinity is the r to the n. If r is bigger than 1 or less than negative 1, then that quantity as n goes to infinity is going to grow unboundedly, which means our limit is going to diverge, and therefore our geometric series diverges. On the other hand, if the absolute value of r is less than 1, in other words, r is a number between negative 1 and 1, As n goes to infinity, that quantity is going to go to 0. And then we'll see that our limit is equal to a over 1 minus r, and hence we have a formula for evaluating our series when the absolute value of r is less than 1. Now you may have noticed we have not evaluated the case when r is equal to 1 or negative 1. They're not particularly interesting. When r is equal to 1, our sequence just becomes the sequence a, comma a, comma a, and so on and so forth. And therefore, the partial sums are just going to be a times n, which are going to grow unboundedly. If a is negative 1, then the sequence itself is going to oscillate between negative and positive values, and the partial sums are going to oscillate as well, which means that the series also diverges for r equals negative 1. Since the value of a geometric series is equal to the limit of its partial sums, we now have this formula. The sum from n equals 0 to infinity of a times r to the n is going to diverge when the absolute value of r is greater than 1, but it will be precisely equal to a over 1 minus r when the absolute value of r is less than 1. Let's put our formula into action by considering the series 1/16 plus 3/64 plus 9 over 256, and so on and so forth. So we're going to notice here that for each term, we're multiplying by 3/4 to get to the next term. That means that our r value is 3/4, and we have the sum from n equals 0 to infinity of 1/16 times 3/4 to the n. Notice the first term is missing a 3/4. That's because it's being raised to the 0 power and is equal to 1. Then we have 1/16 times 3/4, 1/16 times 3/4 times 3/4, and so on and so forth. So this is geometric with an r value of 3/4 and an a value of 1/16. So our sum is going to equal, by our formula, a 1/16 divided by 1 minus r, 1 minus 3/4, so that's 1/16 over 1/4, which is 1/16 times 4 over 1, which gives us 1/4. Okay, in this next example, we are now going to add up 1 plus 1.01 plus 1.01 squared, so that each time we are multiplying by 1.01. So this is going to be the sum from n equals 0 to infinity of 1.01 to the n. And we can see again that that is geometric, but that our r value is 1.01, which is greater than 1, so we know this diverges. And if you think about it, each of the terms of the sequence is greater than 1, and when we add them up, the sum is just going to keep getting larger and larger and larger, and hence diverge. In our next example, we're going to notice that we have a geometric sequence again. This is the sum from k equals 1 to infinity of 2 to the negative 3k, which I find it a little bit easier to think about that as the sum from k equals 1 to infinity of 1 over 2 to the third to the k, which is of course the sum from k equals 1 to infinity of 1/8 to the k. But we need to notice that this is not k equals 0, and that's important because we're missing a term. So there's a couple ways to think about this. The first is to switch the limits of the limits of our sum. So we could say, well, let's let n be equal to k minus 1, so that when k equals 1, we would get n equals 0. Then this becomes the sum from n equals 0 to infinity of 1 over 8 to the n plus 1, because k, this is equivalent to saying that k is equal to n plus 1. Now we have this weird n plus 1, which isn't part of our formula for figuring this out, but we can rewrite this as the sum from n equals 0 to infinity of 1/8 times 1/8 to the n. And now we have a geometric sequence with r equals 1/8 and a equals 1/8. And so this is going to equal a divided by 1 minus a, or 1 minus r, excuse me. So that's 1/8 divided by 7/8, which is 1/8 times 8/7, which is 1/7. Alternately, we could keep it in terms of k, so we could go back to the sum from k equals 1 to infinity of 1 over 8 to the k. And we could say, well, that's the same as the sum from k equals 0 to infinity of 1 over 8 to the k, minus the first term, the term when k is 0, so minus 1/8 to the 0. Just knock off the 0 term, and that will give us the sum starting at 1. This is geometric with r equal to 1/8 and a equal to 1. So this is 1 over 1 minus 1/8. So that's 1 over 7/8, which is 8/7. So we get 8/7 minus 1/8 to 0, which is 1. And that still gives us 1/7. So that was just two different approaches to solving this one, both of which gave us the same answer of 1/7. We're going to do this last example is going to be proving the mathematical fact that the number 0.9 repeating is exactly equal to 1. And we're going to do this using a geometric series. So when we think about the number 0.9 repeating, we have to realize that that is the same as 0.9 plus 0.09 plus 0.009, and so on and so forth. We can keep adding zeros, which is of course 9/10 plus 9 over 100 plus 9 over 1,000, and so on and so forth. And so we can write that as 9/10 times 1 over 10 to the n, and n here is going to go from 0 to infinity. So this is geometric. It's geometric with an r value of 1/10 and an a value of 9/10, which means that that sum is equal to a 9/10. That looks like I wrote an a, so let's make it very clear that that is in fact a 9 over 1 minus r, 1 minus 1/10, which is, guess what, 9/10 divided by 9/10, and of course when we divide a number by itself, we get 1. So we have shown that 0.9 repeating and 1 are in fact identically equal to each other. Okay, we'll just wrap this up with a reminder that the sum from n equals 0 to infinity of a times r to the n, the sum of a geometric series, is going to be a over 1 minus r when r is between -1 and 1, and it's going to diverge otherwise.